seen. So what happens in this home is when the ventilation system is turned off, and it no longer has constant fresh air coming in and exhaust leaving, the home is closed up for 2 days. The total VOC count spiked from a very low level to 3 times the World Health Organization recommended threshold. This peak would be very much like what a home being built to today's airtightness standards would look like without a working ventilation system. And and this one would be on the low side of the VOCs because of the material selection. Um, when the ventilation system is turned back on, you can see the VOC level immediately drops to well below the WHO recommendations, and remained in a very, very healthy range. That healthy range is determined by the volume of the home and the airflow that we put through it, which we'll talk about a little bit later. Um, and you can kind of see in this graph, if we did slow that ventilation rate down, we could expect that VOC number to rise back up, right? So this is a way we're directly affecting the air quality inside the home is by the flow rate, especially in a very tight home. So the message here is even when it's built with the most care in material selection, um, ventilation and a working ventilation system really matters in this case. Thanks. Okay, good. Catching up with myself there. Um, so, so this is really why we like continuous ventilation with distribution. It solves all the problems associated with VOCs and pollutants and gives us the best shot at creating a healthy living space in all conditions for all health statuses, including the young, the aging, and the very sensitive. Balanced ventilation uses a supply fan and an exhaust fan to flow fresh air across the whole building in one continuous flow. Bedrooms and rooms receive constant airflow of fresh air. Baths, laundry, mud rooms, kitchens are constantly flowing stale air out of the building. With steady supply flow flowing in, the air washes from supply points across the transitional zones, like hallways and family rooms, and is pulled into the exhaust rooms and out of the building by the exhaust fan and the negative pressure it creates. The two fans are balanced and constantly running. The amount of steady airflow will keep the home's relative humidity in the optimal zone. It'll dilute the buildup of VOCs and other contaminants and provide lots and lots of fresh air. It works best with today's newer, tighter homes and can be filtered to manage both normal and the extreme conditions, due to smoke that we find in a changing climate. In balanced ventilation systems where we have this dedicated source of fresh air coming in, we can place a whole range of different quality filters across it to filter out, kind of common particles like Title 24 MERV 13 filtration, or step up to activated carbon filter, even HEPA filter across all the supply flows coming in. We can do that at certain times when there are problems, or we can kind of consider doing it all the time. But that's the thing that we can do with balanced ventilation. How much ventilation do I need? The most basic calculations to provide sufficient airflow for occupants are in this chart. This is a code level chart. It meets safe minimum flow that assumes occupancy based on floor area and bedrooms. This really just serves the code minimum. There's a lot more that we can do with airflow calculations to improve conditions, as we'll see later in the ventilation for passive house workshop. In this example, 60 CFM continuous flow works for 2,400 square foot, 3-bedroom home because you can reasonably expect that home to be occupied by 4 people with a minimum required supply rate of 15 CFM per person times 4 people equals 60 CFM. So we've got a steady supply flow calculation there. If the home had 2 baths, the 60 CFM is higher than what we would be required to provide with 2 baths, which is 20 CFM continuous for continuous flow, which would equal 40. So we're above that threshold. If we increase that home to a 3 bath, 20 times 3, would bring us back up to the 60 CFM, matching our supply flow. So we're always in a state of balance, but we're choosing really what drives it. And in some homes, as we get into um, deeper airflow calculations, and maybe in a passive house workshop, we'll find that some homes will be driven by occupancy, 15 CFM per person, or a chart like this, which is really a supply flow calculation. Some homes with lots of areas that we want to provide continuous exhaust, more areas than people, will be driven more by an exhaust ventilation rate. Typically, the projects that I see are heavy on the exhaust ventilation, which tends to drive the numbers up. Maybe advance one slide. I haven't. There we go. Thanks. Okay, so now let's consider the energy impact of continuous ventilation. So continuous ventilation without recovery is just like it's a big hole in the building envelope with a fan taking that conditioned energy that we've created and just blowing it outside of the building. On a cold day, we add BTUs into the home by some means and then blow the BTUs out of the home continuously with exhaust airflow. At the same time, we are blowing out, we're bringing in the same amount of unconditioned fresh air that now needs to be heated back up to room temperature. Once heated, then we kind of repeat that cycle and blow that conditioned air back out of the building. To get an idea of the energy impact of this activity, we'll look at a home with a typical envelope of 2x6 walls with R21 insulation, R38 roof, reasonable windows, a HERS insulation inspection, right? So upgraded insulation, and 22 kilowatts of PV on the roof. With the code minimum exhaust ventilation, pretty good envelope, all those attributes were still, this home is still 2.2 points, EDR points short of Title 24 compliance at the time we did this calculation. This is really down to the ventilation losses of pushing out the conditioned air that was created in the home. If we fix that problem, the home would be back in certification range. The losses, the energy losses through that ventilation without recovery is really that big. And so really what we need to do here is to recover the heat that we're pushing out through the ventilation system. This is where our HRV or ERV will come in. So recovery ventilators, really, as we step back and look at them, they're an appliance we put in the building, but they're literally part of the building edge or part of the thermal envelope in the building. Just like the walls, roof, windows, they are there to provide an environmental separation and to mitigate heat loss or heat gain, right? They're literally part of the thermal envelope. So like most envelope components, the better they are, the better they'll perform. Let's take a look at really how they work. So fresh air comes in from the outdoors, and we'll say it has no heat in a winter heating condition. At the same time, a matching flow of return air is coming back from the kitchens and baths that has heat that we've created in the home. The two streams of air meet in the middle of this device at the heat recovery core or the energy recovery core. As the two systems meet, the return airflow comes into this core and it drops its heat. After it drops its heat, it heads out of the building through the exhaust air. At the same time, the fresh air coming in from the outside of the building that has no heat comes into the core, sees the heat that the return air has dropped in the core, picks that up because nature is always seeking to balance itself. A flow has no energy. There's energy present. There's lots of surface area. We'll talk about how these cores work a little later. And the energy starts moving over to the side that has no energy. That energy is picked up and is carried into the home through the supply air duct. So the better we can manage that transaction, the more energy we can retain inside of the home. So the return air drops its heat at the core. And lastly, this really works in the same way in a winter condition as it would work in a summer condition. In a summer condition, it's hot outside, And we're hoping to keep the home cool at a certain set point. Whether we're applying air conditioning to cool it or not, doesn't really matter. You got two different conditions, right? So you've got warm air coming in from the fresh air outside. It's going to be countered by the cooler flow coming back from the kitchens and baths. That temperature differential is going to meet in the core, and nature's going to seek to balance itself. The high energy or the high amount of energy on the flow coming in from outdoors is going to drop at the core. This stream that doesn't have the energy will pick it up and send it back outside. So the heat on the outside of the building in a heating climate is going to come in, it's going to get dropped, and then it's going to get pulled back out. So as we work through this, um, jumpy slides there. Okay, they've calmed down. Thanks. Let's take a closer look at really kind of how this works. The recovery core, also known as the air-to-air heat exchanger, is where the two air streams, fresh air intake and leaving air, exhaust air, pass by each other with a large amount of surface area and in contact. So large surface area, airflow is in contact, but they never mix. One stream goes one direction in one compartment, the other stream's going in another direction in another compartment. This is what one looks like. So this is a flow of air coming in, and all these plates are separated from this flow of air kind of coming back out. So it's similar in shape: flow, outward flow, flow, outward flow. The two streams never touch, but they have this large surface area to kind of be in proximity. And as they're in proximity, the side that has energy drops that energy to the side that doesn't have energy. Simply how it works. So as that transaction happens, either in a heating climate or a cooling climate, um, that process continues. In an ERV, the humidity moves in the same principle. So in, in homes that have a low relative humidity and we want to conserve whatever moisture that we're creating, which we're going to take a look at in a whole chapter, there's another style core that will kind of do that same transfer. It'll transfer the heat energy as well as the relative humidity, moisture, whatever we want to call it, through, or we'll call it enthalpy, and it'll bring it across the core and send it back. So when we look at the slide that's up right now, most of the industry that we're exposed to for the last 20 years um, it sees the simple cross flow. Doesn't look like this shape. It's a little square tilted on edge. Those cores are not really super well performing. You know, it's got a kind of an efficiency range of 40 to 60%. So that means if I've got 40-degree air coming out and 70 coming in, I'm only going to capture 40 to 60% of that energy that I've created the home. The rest I'm going to lose. So as I move to the left of the slide and the core starts taking on a different shape, the effectiveness of the transfer starts improving. And we got to ask ourselves, like most of the industry is kind of in this low range, simply because the industry and the consumers in our industry has been satisfied with those results because we haven't really been really pushing the envelope and seeing what we can do with net zero buildings or low energy buildings and things like that. As we change our focus, then we start looking at these kind of higher effective rates, 70 to 85 and even up to 95%. And this could be in a single family home or a full on commercial building, residential apartment building, schools, all these applications that use ventilation. So let's take a look at a home that's got a relatively good HRV in it and really kind of how that works. So this is a brand new home built in 2014. It's in the Pacific Northwest, Vancouver, Washington. That's a mild climate. This data was collected by Portland State University through some um, uh, research projects to just kind of gather information on high performance buildings. So this is in April when the home is occupied, but they have not turned on the heating system yet. So this is simply all down to solar gains, occupant using energy, people, refrigerators, things like that, um, and an HRV in this case with roughly 90% recovery. The home, the ventilation rate for the home is zero point 0.3 air changes per hour, which equates to the volume of the air inside the home turned over once every 3 hours, all new, right? So every 3 hours, we've blown out the entire volume of air inside. And really, what we're trying to do is retain all the energy that we've created inside and that we're generating inside. So we're going to take a walk through the data now, and I'm going to kind of tell you about what these lines are on the graph. So the very top line is the temperature at the airflow returning back from the kitchens and baths, right? So these are the flows that are in the conditioned space that we've created energy, and that energy we're going to bring back. We're going to conserve it in the core and then send it back outside. So that's that flow. Next one down is the return flow coming right back out of the recovery device, and that's going to be going to bedrooms, living room, places that people occupy that we distribute fresh air to. Next line down is going to be the air that's leaving the building. It's the exhaust air channel. So in from kitchen and bath, across the core, then outside of the building. And the very bottom line is fresh air coming in from the outdoors. And it would be correct to say that that is the actual outdoor air temperature, right? So fresh air coming in, that's showing your outdoor condition. In this, I'm seeing a low of roughly about 42 degrees on the 14th of April. Generally, it's hovering right around 50 degrees. The inside, with no heating system turned on yet, is floating right about 68 to 70 degrees. And so through this process of recovery and ventilation, the interesting part is the supply flows, that second line down is hovering just a few degrees less than the return air. So we're doing a really, really good job capturing that energy, picking it up in the core, and then redistributing it back to the house. And when those two lines are really close together, that's really what we're looking at. And that's where we can detail a building envelope and start downsizing the mechanical system or just using less energy to condition it while experiencing all this fresh air. But in some occurrences, right, some of the lower performing ventilation units, if they have some poor components, which we won't really get into today, it's really more for the next workshop, you can kind of get this close differential because they kind of leak heat from one side or the other. It's not really a full-on true exchange. You know it's really a full-on true exchange when you've got a lot of airflow leaving the building, but no heat's leaving with it. That's when you know it's really working, because there's lots of ways you can kind of heat incoming airflow when you are in a room with energy, but there's just no way that you can shed it other than recovering it and redirecting it back inside. So the third line down is the outside, is the temperature of the airflow leaving the building. And that is so close to the incoming air that's the actual outdoor air temperature. So when those two lines are really close together, we know that we've got really, really efficient recovery that's actually happening because the energy in the building is just not leaving. It would be exactly the same way if we flipped it and we're in a heating dominated, a cooling dominated situation, and we would just see the numbers inverse. The outdoor air temperature would climb, the exiting air temperature would climb, and then our internal set points would be a little bit lower. So you can infer that this building really in April, we've got low winter sun kind of coming up. We're getting a little blast of heat. It's performing really well. So one little question that I'm going to throw out and pop an answer in the chat box. It's kind of a fun question. So in the very top line, right on the 12th, you can see a line coming along. There's a little spike, and it goes along. Next day, a little spike. But there's a couple of days where you can really see a strong spike on the return airflow. And does anybody want to guess what that is? It's like normal spike. Patrick, nice try. Not solar heat gain. Anybody else want to throw it out there? Generally, we do it once a day. And generally, this airflow is coming in from kitchens and bathrooms. So just to keep moving, uh, yes, you got it. Shower. So that is the shower blip, right? Because when we think about it, we've got a bath. It's got 20 CFM continuous airflow out of it. And when someone showers, you know, other than getting clean, what we're doing is we're taking a whole lot of BTUs out of a tank, dumping them into a room, water drains out, room fills up with steam and heat, and that heat actually shows up on the return air monitoring device. But the really cool part is you can see a corresponding little blip on the supply airflow. So all that little energy pops in through the core, transfers to the other side of the core, and that same most of that energy returns back into the home. That's when we know it's really working, when we can see details like that. So we are going to get to questions at the end of the chapter, and we're really close, a couple of slides away, and then we'll spend a few minutes kind of talking it through. So same example that we looked at before, in terms of kind of this Title 24 calculation, you know, how we're doing. So on the left-hand side, we're back to that same house, and it's exhaust only, no recovery, right? So just a hole in the wall. We shove the energy out of the building with a fan. We've got our usual 2x6, R21, R38 roof, yada, yada, yada. Compare that to the slide on the right, or the home on the right. Now it's 53 CFM, so it's not a really big home, right? It's going to be less than 2,400 square feet. Um, and now we downgrade the building envelope. Instead of 2x6 at R21, it's going to be 2x4 with R13. The roof goes from R38 down to R19. Windows don't really work quite as well, a little lower performing. There's no HERS inspection on the installation install. And the PV goes from 22 kilowatts down to 16 kilowatts, right? So the whole thing is down. But the darn thing is that because we're employing heat recovery on the ventilation losses, big old hole in the wall, that energy, using that with this kind of lesser performing building envelope, would put us into Title 24 compliance. Not at all saying that's what we should do, use HRV so we could use 2x4s and R13. Not the message here at all. It's an illustration. This is a calculation that we did with um, a consultant in California as the new Title 24 is coming out. We looked at single family homes in many different configurations and apartment buildings, and tried to understand what the ventilation losses, and as you increase the scale of effective recovery, what that does to the building envelope, and what kind of what kind of other alternatives, and how can it help you out with the building envelope. If anybody is interested to that in that, reach out to us. There's a whole blog on our Small Planet Supply blog and so forth, kind of explaining it. It's a moving target because California Energy Commission is, you know, trying to kind of keep the game going in the right direction, and we don't want to have uh, heat recovery turn into an argument for really bad building envelopes at all. However, the illustration here is ventilation losses are significant. They're big. And when we think about it, if we go back to that same building envelope, 2x6, R21, R38, 22 kilowatts of PV, all that good stuff, and then we plug in heat recovery, now we're going to find that we're a lot closer to creating a lower energy building, achieving a net zero status with smaller amounts of PV. And if we do have problems with the building, in terms of siting and earth connection, and maybe building envelope imperfections that are really hard to work around, employing higher effective heat recovery is one way to kind of bring that energy balance back in a useful way. Um, so there's one thing about um, the energy impact of recovery ventilation on a building. So energy is one thing and cost is one thing, but you know, we're building these things for people. So let's take a look at really what the comfort impact of using various heat recovery devices, and how we would experience them as people living in the in the home. So here's our example home. We'll place it in my climate, you know, kind of a mild coastal climate, 70 degrees set point inside, 40-degree outside air temperature. And so at 60% effective recovery, we would then get an airflow coming out of the supply going into the bedrooms and public spaces of 58 degrees Fahrenheit. That's kind of cold. It gets a little better as we increase at 70%. So we get a better HRV. That's kind of the way we would fix this. Um, it bumps up to 61 degrees. And it's a simple calculation. We've got a 70-degree set point, 40 degrees coming in. There's a delta T there. 70 minus 40 is 30. And then we multiply that delta T times the effective rate, and that gives us a calculation of what that supply flow temperature is. So there's, you know, not a lot mysterious going on here. If we increase it up to 80%, now we get a supply flow of 64 degrees. So 64 degrees at 15 CFM per person. So maybe like a master bedroom would get 20, 24 CFM, something like that. And if you got 24 CFM of 58-degree air coming in kind of near a bedroom, that's not going to feel so hot when it's 40. It's going to feel worse when it's 30 degrees Fahrenheit outside. But if it's flowing at 64, it's not so bad, right? Because humans are kind of funny. It's not about what we feel on it. Our bodies become uncomfortable in heat loss applications or situations because it's how much our body, how our how much heat our body is losing, which affects how our blood vessels work, and you know whether things kind of tighten up and we start conserving energy at our core. That's really what's going on with heat loss. So the difference between 64 and 58 is like a big reaction in your body. So these things are important. And if we step up to 90%, then here's a really good situation, because if it's 70 and we've got a small flow of 67 degree air, we're never going to feel it. That's going to come in and mix. Well, it's not going to be a cold spot. It could be right near kind of the sleeping area, which means you got lots of fresh air coming in. So you don't have to worry about high CO2 spikes as you kind of close the bedroom door or something like that. It's a really good situation. So when we consider the long-term satisfaction of the occupant in using this ventilation system, as they get more efficient, there's a real benefit for the people that have occupied the space. So now we've kind of gone through that chapter. Now let's take some questions. Um, and so, Patrick, you did have that one question still in the chat box. Where's the rest of the heat coming from? So in that, I know that building. I've been in that building. It's a it's a very good building, 2x6 construction. Believe it's back insulation, really good air tightness. Hit that legendary 0.6 ACH 50, kind of the passive house number. And then I think it's got 1 inch, maybe an inch and a half of polyiso around the edge of the building. Some really good windows. And it's got a lot of glazing. And in April, right, low winter sun kind of coming in, dumping some warmth in that building, because you can kind of go back and remember that slide. It's like the outdoor air temperature was cycling pretty heavy. So in the daytime, we got a lot of heat. Building kind of holds its heat, and the ventilation doesn't cause it to lose heat. And the rest of the heat contribution is really refrigerators depending on the refrigerator you buy, they're basically removing the heat from inside your refrigerator box and placing it outside, out the back through that grill. Every time you run a washing machine, do a shower, just your body walking around and doing things, that all makes heat inside the home. And, as you get into these highly performing buildings, those little heat inputs become more important and a direct part of the calculation in kind of the load balance. So another question pop up: are climate zones a factor for using HRVs, ERVs? Absolutely are. We've got actually a full chapter on it coming up next. So I'm gonna kind of defer to some useful slides to talk about that. Anybody else want to throw anything out there? I'm just gonna take a quick slug of water. Okay, if there's nothing else, we'll keep moving. Um, kind of. So Patrick is asking, will you be addressing cooling during warm months? Um, I think I will. And there's a slide that we're going to pause and talk about that. So we'll get to that slide, and gives me a kind of a better set of tools to kind of describe and talk about. So here we go. Next subject is really going to be enthalpy recovery. And so enthalpy recovery is funny name. I always kind of struggle with it and still kind of like, why are we using that in this context? But okay, that's what the industry uses. That's what we'll talk about. So enthalpy recovery is the ERV. It's the E in ERV. So there's an HRV, and that's really simple, heat recovery ventilator. And an ERV is enthalpy recovery ventilator. And enthalpy is moisture. It gets called enthalpy because this humidity, this moisture kind of changes its energy density. And as the temperature increases and decreases, it actually kind of changes the energy content. And in some ways, as we look at how we calculate some of the values associated with ventilation and energy transfer and so forth, that's an important figure. For us right now, enthalpy recovery is really, we're just going to talk about moisture, um, and that moisture is really humidity inside the home. So we live in California's got a lot of climates. Our North America has just lots of climates, and really all conditions. And California's got a lot of conditions that anybody could be addressing. So we can manage humidity in a home through ventilation. And in the earlier workshop, the relative humidity in the home is super important, right? A super dry home, up in Tahoe in the middle of winter, you know, your lips are getting chapped and all those things. That's something we want to manage. And if we drop a house right onto the coast, just off the ocean, you know, kind of central coast or something like that, there's a whole lot of humidity. And if we bring all that humidity inside the home and we don't manage it somehow, that could be a problem. So, in climates where outdoor humidity is low, usually low to moderate, indoor humidity can be effectively controlled by bringing in outdoor air and exhausting stale air, right? We've got a box, bring in air, exhaust stale air, and we can manage it that way. There are more ways. Essentially, diluting the indoor air with outdoor air when the outdoor when outdoor humidity levels and indoor humidity levels sources are known and the values are known, we can predict the indoor humidity level. And that's kind of part of the calculus of the airflow. Back a few slides ago when we said 2,400 square feet, you know, 3 bedrooms, 60 CFM. The humidity level is part of that calculus also. It's the same in climates where the outdoor humidity is really high. High outdoor humidity can be experienced in many places. For an extreme example, you know, just think of Atlanta, Georgia, when we talk about kind of high humidity areas, high heat, high humidity. We can manage the indoor humidity with a tight envelope and the way that we deliver the ventilation. So we're going to walk through a couple of slides and then we'll start kind of capturing all of this together. Um, so we make moisture in homes. We constantly produce moisture in our home just by living in them. We can count on a continuous contribution of moisture and generally predict how much moisture that will be. As we move air in and out of the home, we can increase or decrease the home's relative humidity by how much air we move through it. With a fixed amount of internal moisture contribution, as we can kind of see in this chart, if you move dry air through that home, it will blow out the moisture that you contributed and tend to dry it out, right? If there's dry air coming in and we're blowing out the or the fixed amount of moisture that we're creating in that home, we're generally going to be reducing or drying out the home. If you blow in humid air, into the home, it will add to the internal contribution of moisture that's always there in kind of a steady state, and the relative humidity level of the home is generally going to increase. So the rate of flow, airflow, and the humidity of the air that you flow into the home really matters, and it will affect the home's relative humidity level, therefore its comfort and the occupant's health. If things get too dry, it's unhealthy. If things get too humid, it gets unhealthy. Kind of the first workshop we did had a chart kind of showing the two guardrails for that. Let's see just how airflow really manages this. We'll start with airflow and then we're going to start looking at enthalpy recovery. So just to get the basics down, here's a home. Consider it a box right here in front of us. We've got two fans. Fan A is pushing air in, fan B is pulling air out. So so we'll say the outdoor air right now is high humidity. You know, it's cold in the heating season right now. This example showing 23 outside with 90% relative humidity. It's a strange situation to be, but it is a calculus. It does exist. And on the inside, we have a contribution through just living and breathing and doing all the things we do as humans of 330 grams per hour of moisture contribution. That's, we just create that on an average on a steady basis. Our inside set point is 68 degrees Fahrenheit. And in that condition, we can expect 24% relative humidity. And the reason that relative humidity is coming down to 24%, even though we've got high humidity on the outside, is there's two driving factors. We're only making 330 grams per hour of moisture, and we're pushing a lot of air through it. And the funny thing is, 23-degree air outside at 90% relative humidity, you know, it's called relative humidity because it's relative to the temperature. It's like little air grams, molecules that are suspended in this gaseous air. And when the air is cold, you know, when the temperature is cold, right, everything's kind of pushed together. And so the volume of air relative to the amount or the volume of moisture, sorry, relative to the amount of air in that little space is a lot. But when you warm that air, you bring it into a 68-degree environment, then the air expands. And as it expands, you've got a fixed amount of moisture in it because that's really measured in grams. There's another measurement. I can't think of what it is right now. But then as the air expands, the relative amount of water to the volume of air starts dropping. So 90% comes in, it'll come in and at 68 degrees, it'll turn into, you know, like 50% or something like that. And if you've got 50% relative humidity kind of coming in at a and clipping at 135 CFM every minute, and you're only making 330 grams, then what you're making here is just going to get blown out of the building. So the relative humidity is going to drop. We advance it. We change something. So one thing that we can change is we can't change the environmental concerns. We keep our set point at 68, but we lower the fan speed. So we go from 135 CFM airflow and we ramp it down to 44 CFM, which means that we're less than a 2,400 square foot home. Never mind kind of what our guardrail limits are, just in understanding kind of how this transaction works. We lower down to 44 CFM. And you can see that the relative humidity pops up to 41%. 41% is comfortable. 24% is not comfortable. We have these conversations all the time in very, very well-defined buildings in California, in the north in Canada, kind of all over the place. 41% is great. 24% is not great. And this is a factor that's really easy to change. We can just change how much the airflow is. And as long as it meets the other criteria that we're trying to hit, then that's all good. But there's one other thing that we can adjust based on conditions that we experience and design for, is we can use an enthalpy recovery core, right? Rather than an HRV, we'll use an ERV. And so here's kind of a diagram of how an ERV works. There's one more slide that kind of steps a little bit deeper into the plate. So this is kind of a two-step explanation. So the red line is the extract air. And in a winter condition, generally in a winter condition, we're trying to increase the amount of moisture in kind of like the Tahoe region, maybe not the coastal region, but kind of think about the Tahoe region right now, where it's dry outside. We're not making a lot of moisture inside. We need a flow of air, and so we're tending to dry the home out just with simple airflow. But if we pop kind of another recovery device in front of it, an enthalpy core, actually recovers the moisture at the same time. So that red line, the moisture comes into the core, starts transferring over to the other flow, just like the heat transfers over to the other flow, and then returns back in. And again, just like heat, the amount of enthalpy or moisture that we can recover depends on the quality of the core. And they come in all shapes and sizes. Some are really pretty crappy, and some are really quite good. So if we want to really recover the humidity and the heat recovery, this combined with changing the airflow will change the dynamics of the relative humidity inside the home. So we can take kind of a deeper dive in this. Um, Kind of think maybe of Gore-Tex, but Gore-Tex doesn't really have enough density. Kind of get to that where I'm going with this. It's a little mystery in my own mind right now. So just like HRV, an ERV has two streams of air moving in opposite directions. The plate separating the airflows will also absorb moisture in this case. In an HRV, they only absorb heat. The flow that has moisture coming back in, when it encounters the membrane with the flow that doesn't have moisture coming in, just like heat, the moisture will get dropped and nature will seek to balance itself. The moisture will essentially wick over to the other side where the airflow has less moisture, and that moisture will get picked up in its flow back inside of the building. The amount of moisture transfer depends on how good the recovery core is. And these days the cores can get pretty good with as much as 90% enthalpy recovery. And so this is a key way that we would manage the home's relative humidity in really dry climates or really humid climates. It works kind of everywhere in between, but as we get to kind of the extreme outer edges, it really matters a great deal. So here's where we can kind of talk about cooling and how it affects an HRV core and an ERV core. So this slide shows a winter scenario and a summer scenario. The winter scenario is relatively simple. We've talked about it a couple of times. My upper left, on the left-hand side of the screen, winter scenario, upper left column in yellow or gold, we've got 68 coming in, and then it's heading back outside of the building after it leaves the core at 38, while we've got 32-degree Fahrenheit air coming in from outdoors, passing through the core, and we're returning 63 degrees back into the supply flow. We're right around something like 90%. We could do a calculation. So we're losing roughly 5-degree Fahrenheit in that transaction. And we're losing maybe 6 degrees on the other side. So those numbers are lining up pretty well. That's probably really realistic if we put some monitoring devices on that transaction. So that means all of that energy that we're creating, most of it's staying inside of the building. So now let's switch to a summer scenario, and let's switch to hot and humid and an ERV core. So counterflow ERV core. This is quite a good core, 90% recovery. So same scenario, right? 60 degrees coming in, and the only way, and sorry, 104 coming in from outside, right? And it's humid. So in my understanding, unless we've got a really, really good building, the only way we're having a 68-degree coming back from kind of kitchens and baths on when it's 104 degrees outside, we're either underground or we've got cooling going on, right? So we're cooling the building. And as we're cooling it, we tend to dry out the building because as we drop the temperature, the relative humidity drops. And so we're kind of pushing that in, and we can do that really well, or we can do that in a clumsy way with, kind of a clunky AC device that just starts up, cools, shuts off, warms up again, cools, shuts off, right? Either way, doesn't matter. 104 coming in, 68 going, kind of coming back in from beds and bath, and we put a lot of energy to cool that down. So enthalpy recovery is going to be really helpful here, because if you look down below the 104, what we've got is 97-degree air leaving the building. So most of that energy is staying outside and most of the humidity is staying outside because the enthalpy recovery core is just like a heat recovery core. It's part of the thermal envelope of the building, but it's also kind of part of the moisture envelope of the building. And in this case, in high humidity outdoor conditions, you want to keep the humidity outside. And that's what a good quality core is going to do. If we want to reverse it, where it's super dry outside, and we just built uh, a custom home up in the Tahoe or Reno area, and we're putting two adults into 3,500 square feet in high altitude, cold conditions. Well, here's what's going to go on. 3,200 square feet, we're going to need a lot of airflow because part of our air calculation is based on volume. Two people in a home in that big of a box aren't going to make much moisture. I mean, there's just not enough people to make a lot of moisture in there, right? So high airflow, small moisture contribution in a dry climate, we're going to tend we're going to be in a home with very low humidity, and that's where you see applications. People will add a humidity device, something to kind of bring up the humidity in the home and so forth. So one thing we can do is we need that airflow, and it's kind of counterproductive to add another device to generate more humidity in there. So we'd want a really good enthalpy core in that winter condition to maintain a high level, or as high, conserve as much humidity inside the building as we can, so that we don't need another system to add more. It's not going to be a perfect system. It's a balance. It's the penalty of two people in a large space, not contributing much moisture. And you have to kind of work on those, but those are really significant tools that you can work with. Um, so how are we doing on a couple more slides, and then we'll ask and we can bounce back a couple of slides. So that's kind of the example of HRV to ERV and a hot, humid climate and a dry climate. So ERVs are really a useful tool when it's really dry or when it's really humid. And it's a mixed situation. If I was building something on the Central Coast in California, or anywhere on the coast in California, because we get into these kind of small microclimates and some decisions that are just kind of hard to make, but the boundaries are so similar. It's not like we're going to make a mistake and do something wrong. It's just not understanding exactly what's perfect. So there's a map for this, and broadly we can kind of go by the map, and broadly it'll get us there. If we actually want to really detail how the conditions of the house um, are going to be for the occupants, I wouldn't be using the map. But the map's a fine place to start. The map basically says it's blue. Blue is cold and dry. We need an ERV because generally we're going to be fighting to keep the relative humidity up in a home in a cold climate. Anything below green, down through, and right now Texas is more blue than it is orange right now today, but still going to be kind of the same case. In those southern parts of the continent, where they're generally more hot and more humid. Certainly in the orange areas, so that's an ERV again. The green area is really right about an HRV, HRV ERV, because it's kind of that close decision point, and you kind of dig deeper into it. The coastal green is also HRV or ERV, and and here's kind of some of the decision points. This is where if you want to, you work with a good partner that understands the situation a little better. Again, coastal California, a family of six in 1,800 square feet. Family of six, 1,800 square feet, more people, more moisture contribution on a coast. A lot of moisture outside there too. It might be a case where an HRV really makes sense because at least the cold air coming in that has high humidity is going to warm, and that humidity will drop. And the main function is we might have more humidity generated in the home than we can manage, and we want to push that out. And if we want to push it out, then we don't want enthalpy recovery. We just want to push it out. Conversely, a couple of people on the coast in California in a large building envelope, ERV might really be better because they're not going to be making a lot of moisture inside the house. And we've got kind of coastal conditions where at times there's high humidity and fog and things like that, but it'll warm up. The relative humidity will drop inside the house, and maybe having that enthalpy boundary around the building envelope will kind of keep things a little bit stable inside the home. Those are kind of the decision points that can be made, and it's just, do you have kind of the right conversation going on to make those? So now it's time for questions, and it looks like Dee popped a good one up there. How does the core add moisture in that example of two people in 3,200 square foot in dry winter conditions? Thank you. The core does not add moisture. It only conserves the moisture that's already in there. So if I go back and I try to use my hands to explain this, um, so we've got a box right here, and we got the edges of the box, and there's very little moisture outside, and we're flowing that moisture inside. And then we've got two people inside of our box, and they're making a little bit of moisture, not a lot. And so, really, what that enthalpy core is going to do is prevent that moisture from leaving. It's going to kind of hit that enthalpy wall and circle back and stay inside the home. And so, what it can do is not, it can't generate anything because there's no moving parts and there's no hose going in there. It's just going to conserve what's already um, um, missed, or sorry, conserve what's already created. And if it's too dry in homes like this, then you need to add humidification, right? So you would add a humidity device to just bring up the relative humidity and set it on a signal that it kind of manages itself. So Peter, you may have missed this, but is the incoming air filtered in some way? So I'm going to say yes, and thanks. This is a great question. There's a slide later, but we're going to do this right now also. So, like all things that we work with in this industry, things come in different quality levels. So you can buy a $900 ERV or an HRV, and in it it will have a filter. Title 24 is requiring filters kind of at a higher level right now than most manufacturers have been offering. But you can also buy an ERV for a whole lot more money, like 2,500 bucks or something like that, um, that is a lot more efficient and has a different filter. So the $900 filter, it's a filter that you kind of take out, and it's kind of this plasticky thing that you could use in a forced air system, right? It's it's not a super good filter, but let a lot of air pass through without creating static pressure, which is kind of what that device wants. Some of these filters will also clean a barbecue grill pretty well, if that kind of gives you how suitable they are for filters. Um, in the better units, there are really good filters. That's a really good filter. That's a pretty good filter. Actually, this is not even suitable for a supply flow in the state of California right now. It's a G4 filter, which is a MERV 7 or 8. And Title 24 brought in MERV 13, which is super good. MERV 13 will filter out most of the things that people are sensitive to in terms of allergens and things like that. It won't do viruses, but it's really good filtration level. It won't do wood smoke. Um, you'll need additional filtration on that. But the nice thing about ERVs or HRVs, whatever filtration comes with them, you can add another box on the outside. There's a picture of one. So you've got a building, you've got a supply flow where you're bringing in fresh air, and you can add another box on that. Actually, it kind of goes on the warm side to be proper about this. It wouldn't go between the outside of the building and the ERV, because when it gets cold, um, it'll get cold, you get some moisture buildup, and you could actually get a layer of frost on the filter itself. But after it goes through the heat recovery core, even when it's freezing outside, we go through heat recovery, and now we're always above freezing on the flow to the house. So that's where you would actually put another box with a filter. This filter is an activated carbon filter. So this is what would get rid of wood smoke. It gets rid of things you can smell in wood smoke, but filtration at this level is funny. You actually want to get into HEPA and MERV 15, which is filtration you can add as a separate device, because all of these conditions are relatively new. So to kind of recap, you can hit Title 24 most of the time by carefully choosing the equipment, because they'll have addressed how to how to supply MERV 13 filters with the unit. If you want to go deeper with filters, you can. It's an extra device, an extra conversation, and it can work really, really well. I've done it myself, and we've got some data monitoring set up. So next year we'll have even more data. Do ERVs need to be serviced, or do transfer plates need replacing more than HRVs? You know, I can only give my personal answer on this one. So I work with the good stuff. That's just kind of who we are in the company I work in. So with the good stuff, um, I think we would need the highest level of service. And in core servicing, we're recommending once every 5 years. And to clean a core, because in the in the good units, there's filtration on both sides, right? Fresh air has got a filter, even around that frost issue, but we've got a way to manage that. So it's right at the unit. So we're filtering out bugs and leaves and kind of all the big stuff. And then the flows that go to the room or come back from the room, sorry, have a filter in front of it also to pick up cat fur and just anything in the home. So, and the goal of those is for this to stay clean. Yes, it's kind of about people, but it's also about long-term performance. So this guy stays pretty clean. When it comes time to clean it out, in all of these devices, you would pull it out, lay it down, hose it down with a hose and a little bit of water pressure. You can put just kind of a really gentle soap on it or something like that. Shake it out, let it dry out. It does have airflow in it, so you can put it back in, turn the unit on. The airflow is going to pull the moisture out. In an ERV, probably better to just let it dry out a day before putting it back in. And that's a level of service. HRVs and ERVs, the big commitment is change the filters. Even in the poorly performing ones, it's important to look at the filters and change it. If you really want to take advantage of high performing units with high performing cores, you really want to look at those filters and refresh them twice a year at least. The things that drive this heat transfer, the 90% or something like that, is two streams of air moving at the same rate. When they move at the same rate, the energy balance is the same. It's not like one's moving faster than the other and then they don't really get a chance to kind of exchange that energy. They got to be moving at kind of the right speed. That's how they're sized for small, medium, and large home. And when they're moving at the same speed, they work really well. So the filtration um, tends to get blocked up over time. And as it gets blocked up, it increases static pressure, which will slow one stream down. So part of the whole maintenance schedule is just check it twice a year. There's really nothing else you need to do. Maybe clean that. Well, not maybe. Certainly inspect and clean it, once every 5 years. But the filters are, 2 times a year at minimum. Great. No more questions. Any more questions just on this chapter? Take a brief drink of water and kind of slow it down so you're not, getting bombarded by too many words. Good. We're going to keep moving. All right, we got 2 more chapters. I'm going to kind of move through it. So these are the key points, and the next section is a smaller section. So we'll kind of talk about this. There are parts of the state that you could be, or in the country, where you could be putting projects together, and frost prevention is really an issue. So again, the issue here is when it's freezing outside, and we've got moisture coming inside, and we've got two flows of air. What we really need to do is make sure that this that that the core doesn't freeze up. There's kind of 2 ways to manage that. There's kind of a, I'll let you decide which way we like. There's defrost by recirculation. So defrost by recirculation. One flow of air coming back 70 degrees from kitchens and baths. And here it's going to be leaving as cold as it possibly can be, so if it's freezing outside, it's going to be leaving a couple of degrees above freezing. Fresh air, freezing, coming in here, maybe a little bit below, and we're going to recover it. And then we're going to have, this is our fresh air coming back in. So when this is below zero and there's moisture present, there's a potential of buildup ice inside of the core. So the cheapest and easiest way to deal with that is to take the energy that's coming back from the kitchens and bath and just kind of wash it through the core, um, but kind of create a little cheater valve that takes some of this warm air and recirculates it on the fresh air side. So we're taking the stuff that we would normally exhaust out of the building from the bathroom or the kitchen, and we're reintroducing it onto the supply slide side along with this air that's below freezing. And so the two air streams mix and they bring up the temperature right here to just enough to keep it from freezing. So that certainly works, and that's kind of where the industry has been for years and years. And even the Canadian HRV standards are kind of written to make that work really well. In a passive house, not that this is a passive house chapter, that would never, ever, ever, ever fly. We would never take exhaust and reintroduce it to supply and bring your bath, the air from kitchens and bath, and put it back into your bedroom. Verboten, never going to happen. So the other way that we manage this is a simple way. We take the freezing air that we're just to just above freezing, right around 32 degrees Fahrenheit. At 32 degrees Fahrenheit, with um, 68 degree or 70 degree air coming in here, we're going to kind of warm the assembly, and we're not going to develop frost. That's kind of a magic number. So all we need to do is provide a small amount of lift. So to provide that small amount of lift, we are going to, so here, there's a nice slide that talks about kind of return air leaves the building 100% fresh and no normal flows, system in balanced state. And that's how it's normally working. When it gets cold in recirculation imbalance, that's where we're kind of rechanneling some of that return air back into our supply air. And so if we don't want to do that, if we want to lift above freezing, there's a number of ways we can do this. So here's the ways, quickly and simply. So this is an electric preheater. In cold climates, mountainous conditions, or anywhere it's cold, even in high desert applications, this is an electric preheater. So this would be parked between the building envelope and the HRV ERV. We've got a little electric preheater. They come in all shapes and sizes. Some of them are smarter than others, and they'll look at the incoming flow temperature, and they'll have like maybe a 2 kilowatt heating element in it or something like that, and they'll start flashing energy and try to lift the incoming airstream to something above freezing. The cheaper ones will tend to overshoot, and so you could wind up taking 28 degree air and lifting it to 40 degrees because you've got an oversized heater there. And that's okay. Everything's still working. The ERV is going to work all just fine. It's just that, you got a little bit of energy that you're wasting, because essentially what's going to happen is that energy is going to wind up getting bounced outside. It's not going to be heating energy that shows up inside, because we've got a core here that kind of redirects things. So it's nice when they work in the range that they're supposed to work. Here's one that's really, really smart, that works on systems that I understand and work with, and is suitable for these low energy buildings where we're really living on a thin energy margin. So that little red circle that drifted up there, that top red line is the after preheater. And the lower line is kind of the outdoor air temperature bouncing around. So the goal is, and this is going to be in Celsius, the red line's at 0, right? So that's freezing, 32 degrees Fahrenheit. -5 is, it's probably something like 28 or 26 degrees Fahrenheit, something like that. And so essentially what that's going to do is it's looking at the conditions, it's looking at how much airflow and what the relative humidity of the incoming air is, and it's doing a calculation to flash just enough electric energy onto that preheater, onto that electric element to lift it to zero as it flows through. And it really does work. I've got equipment where I can see how well it's working, and it tracks right around there. And so on a project, if you're living on a tight energy balance, this is a super good way to manage it, because you always have fresh air, no mixing of streams, and you're just using the energy that you need to maintain it. If you want to take it even farther, um, and oh, so one more slide to kind of talk about. So if we talk about the energy penalty, if we look at exhaust only energy and kind of some levels of preheater, so if we heat up a home with a forced air system or a mini split or something like that, we spend a lot of energy heating that up. We lift it all the way up to 70 or something like that, and that represents some level of energy, 4,000 BTU an hour, something like that. And if we're going to conserve, if we're just blowing that energy out, then at 53 CFM continuous, then those BTUs are leaving. They're never coming back. We've just expended them in order to provide ventilation for the building. If we start putting a preheater in line and it uses electric energy and it's not perfect, the sum of energy that it uses in the preheating function is still a lot less than what it would use without a preheating function. So we wind up saving a substantial amount of energy. The best way to accomplish this is super simple. There's a little bit of cost to it, but essentially it's a ground loop. So you just run a ground loop of 300 feet around the foundation of the building below the frost line, right? So something where it's going to, hopefully be, 40 degrees to 50 degrees temperature, something like that. Run a brine loop through the run a brine loop um, uh, through the loop around there, and run that brine loop up to a box that sits right in front of the HRV. So we bring the energy up from the soil, put it in front of the airflow coming into the building, and away we go. Okay, no questions right now. We're getting kind of short on time, so I'm just going to kind of jump into the last chapter right now. And the last chapter is uh, how to set up an ERV or HRV into a building. And so there's a few things you want to do. These are just really important subjects. Um, Typically place the unit near the building edge so that you don't have to run these insulated ducts carrying this very cold air. When it's cold coming in, it's going to be cold going back out. So the closer you get to the edge of the wall, the simpler. And it does have filters. Filters want to be changed, so just locate it in a space where the homeowner can get to it and regularly change the filters. In a crawl space can be a problem for that. In an attic can be a problem for that. Good units with filter changes will create really comfortable homes, so it's worth giving it a good spot. Um, Ducting coming in from the outside of the building absolutely needs to have insulation on it, really in all conditions, because two things. One is we've got cold air coming in, and that cold air can transfer into the home through the ducting, but it'll also make condensation, right? If we have cold air coming in, not necessarily freezing, just cold air coming in into a space with that 70 degrees and it's got moisture on it, that moisture is going to hit that cold surface, water is going to build up. So you want insulation to protect from condensation. And as you insulate, you want to make sure you have the vapor barrier around the insulation so airflow can't get to it. When insulation gets wet and soggy, it really creates kind of a mess. HRVs and ERVs, but HRVs absolutely use a condensation drain. Cold air coming in that has some moisture, um, and cold air coming in is cold. Hot moisture coming back from showers and so forth is going to hit that. In an HRV, that transaction is going to push all the water out of that airflow, and that water is not going to get redirected back in the house in an HRV. It's going to turn into liquid water and fall out the condensation drain. You would be surprised at how much condensation a really good HRV makes, because at 50 to 60%, it drops some condensation down. At 90%, it drops a lot of condensation down. There's two ways condensation drains work. Some of them use a ball trap with plumbing that can connect off to a drain. The less expensive kind of common industry units use two little flexible hoses, and you create that you create a little loop that kind of acts as a P trap. Okay, good. Um, so now we get to kind of a really important point about HRVs and ERVs um, in homes and balanced ventilation, is how we distribute the air. This is really kind of a crux of how the system works. So this diagram, the red lines are supply flows. And I'm going to catch myself up. Yeah, the HRV is in a closet, or ERV, not near the building edge, which is where I suggested. So we got to put them where we got to put them, right? So the red line is the supply flow. So we run some supply flow into all those bedrooms. Some of the bedrooms have two red lines and some of them have one. So in our nomenclature, what I'm used to is each one of those red lines is maybe 12 CFM. And in a master bedroom, we generally have two people. So we'd want to have kind of 20 CFM or maybe a little more. In the other bedroom, another 20 CFM. In a single bedroom that's partially occupied or is just maybe one child, a small human, one one flow of 12 CFM is probably fine. And we need matching return flows for this. And so we're going to place the return flow into the bath, as you can see. We'll also place it kind of around the kitchen where we're kind of picking up that moisture, never right over the cooktop. We don't want to capture grease directly into that airflow. Want to be, 8 feet or quite a ways away from kind of the cooking surfaces. And and you notice we're not really throwing a lot of fresh air into the living room. I see one, um, yeah, I don't see any flowing into the actual living room. And that's the reason is because if in a sleeping area in a bedroom we need maybe 20 CFM for a two-person bedroom, and there's another two-person bedroom, maybe there's bunk beds or something, so another 20 CFM, that's 40 CFM, and then another single occupancy bedroom, 10 or 12 CFM. Now we're up to 52 CFM. And in a 2,400 square feet, our recommended flows are going to be right around 60 CFM. And this is 3 bedrooms. It might be that size. It looks like it's an apartment, actually, so it might be a little bit smaller. And really, kind of the point is all of that air is going to the bedrooms rather than the living room, because that's really where we need most of the airflow. And what's going to happen is in those bedrooms, those are positive pressure points. So we're pushing air into those points, while at the same time, somewhere else in the building, we're creating negative pressure points all the way across that living room, in a bathroom, or kind of around the corner in the kitchen. And it's just going to be a simple transitional pathway where we positively pressurize the bedroom, it transitions through the halls and living room area, and then gets picked up in the negative pressure area and pulled out of the building through the return ducts. So we are essentially employing a cascading design across the whole building, starting in the bedrooms, because as we close the door, we get lots of fresh air coming in. It travels through the undercut of the door at night and leads to the outside of the building. As we install ducting, we want to be careful. There's a filter. Filter's a great thing. It's on the warm side of the HRV in this case. The filter is going to add static pressure. And when we use flex duct, um, that and the flex duct gets kinked later or in construction and we don't inspect it, that creates static pressure also. So the quality of our airflow is going to be dictated by the quality of the installation and anticipating what kind of static we're introducing into the system. You can transition airflow from one unit to another. I've got certain regions that we work with where there's a big main house and there's always kind of a mother-in-law apartment, a little rental unit or something like that. They'll employ one big HRV and then a 4-inch duct or a 6-inch duct through a fire boundary with a um, smoke or a fire damper, uh, and everybody will run off of that one airflow. It's great to do that in the good equipment because we're never recirculating anyone's exhaust, right? So the exhaust in the rental bathroom is never showing up in the master bedroom supply flow because the better units don't use recirculation as a way to do frost prevention. Sorry, it's always 100% fresh air. So what everybody gets in those areas, 100% fresh air, everyone's exhaust always leaves the building. As you're introducing ducting, there's there's steel ducting, there's flex ducting, and there's also small diameter ducting like this right behind me. So this ducting system is designed around roughly 12 to 15 CFM per tube, and you create a manifold right at the unit, and it's called a home run rather than a trunk and branch where we run a big, large diameter steel line down and make branches and come off. Everything is a home run from the unit to the actual supply point or return point. It's nice and clean and simple. It's really easy to balance at the end because, getting airflow to kind of move down a central corridor in a trunk and then take a hard 90 and show up at a certain value, another 6 feet with another 90 around the bend can be kind of tricky. So that's one way to do it. What you don't want to do is make a ductopus. I actually had to go straighten this one out. This is an apartment building in Seattle. The HRV is down below, and that steel box in the middle is a heating and cooling coil. And so the idea is that the air comes out of the HRV, passes over that coil, gets lifted or dropped in air temperature, and then distributes out to the apartments that it serves. This device serves about 5 apartments. They didn't leave enough room. It's really hard to figure out how it plumbed. And you can imagine that, okay, we can design it, we can put all the parts in. It's another matter whether they actually work. And we have the ability to kind of get the airflow where it's going. So good planning, good materials, good installation is really important. The people that did this are really good people. They just let the situation get ahead of them. We work with residential buildings and big buildings, office buildings, rental apartment units, condominium high-rise units. It's all the same. You can approach it with single HRVs or ERVs in a single home, in a single apartment, or you can have a big office tower and a really large HRV. Same principle, maybe different delivery method. Um, on the left-hand side, you can see where we're coming from. And the new term is called DOAS. So this is a system that's got kind of the gray box on the outside that just kind of brings air up, brings a little bit of fresh air in. That's that little blue line. And then it's got a gas heater or an air conditioner or something like that. And it lifts the temperature and sends it back inside the building. Um, and in that building, we're just using the air over and over and over. We don't have much fresh air coming in. The building next to it now uses a very large heat recovery device. It's the same principle in that we're conditioning the energy and we're going to run it through a core before we run the stale air outside and bring fresh air inside. We're going to recover that energy and everyone's going to get um, lots and lots of fresh air. So we'll be more productive in our work and conserve the amount of energy inside the building. And the term is DOAS. It's becoming a common term now. It's now Washington State Code for residential apartment buildings, and I think it's coming on for commercial buildings and new construction right now. It's going to be the same in California. Dedicated outdoor air source, DOAS, same as single family HRV. And now that we're kind of in a COVID environment, the big concern is that in the building on the left that we built quite a long time ago, we're recirculating the air. So the only way we can deal with the virus is to put in filtration. And putting in filtration and capturing it all and redistributing at the rate that we need to do is a really big challenge. In new projects, the building on the right is going to have a lot of fresh airflow. It's going to have a lot of exhaust flow, and it won't have the energy penalty that we would typically associate from it. So absolutely kind of the bright picture of the future. Last thing that we're going to do with this is we're going to look at commissioning and balancing. It wants to be done by someone who's used to doing it. It's not terribly simple. All we're going to do is look at the two flows, inside and outside, and make sure the flows are the same and within the range of our design. In the common kind of basic industry units, they'll use a little device that measures static pressure, and they'll kind of game, what the airflow across the unit is. In the better projects, and as you get into passive house, you'll actually go to each termination and put an airflow meter on it, and you'll adjust each termination as well as the airflows across the unit themselves. Simple enough to do. Doesn't matter if it's a little building or a big building. That building right there has a series of large HRVs across the top. The blue line represents supply flow to all those apartments on 5 floors, and the blue line is kind of the return going back up to the building. When it comes time to balance those things, we've got 2 exhaust fans, and we can really balance them well because it's quite a good piece of equipment that gives us a lot of ability to adjust and set its performance. Without doing anything, you can kind of see that on one side, we've got 181 CFM of exhaust on supply and 178 on exhaust. We want to get it closer than that, and we can get it closer than that just by dialing up the exhaust fan or dialing down the supply fan just a few percentage points to get those 2 numbers to meet. We were able to get those to meet, and in these designs, it's quite possible to kind of on a large building, set a standard and an expectation of kind of my duct pressure, my static pressure across the whole ventilation system is going to be 0.8 water column, 0.8 inches of water column, or, if you want to talk about it in pascals, whatever number. And when it all goes in and we measure it at commissioning and we find these relative values, we know that there's probably not a lot of duct leakage, and that we're getting the right airflow, and that airflow will maintain as long as we keep the filters going. We'll still be in good shape. So with that, I've kind of went through all the topics. And here's a question. Does the type of ducting impact the HRV or ERV system's efficiency? So it does, as long as it's within a realm. So the ducting introduces pressure, right? So as it's just like pushing water through a hose. The more wavy we make the hose and push the water around corners and things like that. So essentially, we want to provide good, clean, and straight ducting as much as possible. And if we're going to make a bend in steel or flex duct or anything like that, we don't want to do bends like that. We want to do bends like that create the smallest amount of static pressure. And when we do that, if we're hitting our designs, everything will work really well. In cases where that building that we saw that we had to go in and fix with the ductopus, that's really a problem. So that really did affect that. And the reason I had to go there is they just couldn't get the airflow out. And it's obvious they couldn't get the airflow out because it was just encountering a ton of pressure before it even left the closet that it was in. And every time we've got a little corner and they're packed in so quite tightly, we have leakage, right? All those little joints had leaks. You can't get the sealant in the back to know that you've got it sealed. And essentially, you've got a fan pushing air through a duct. And if there's a leak, the air is not going to continue out of the duct. It's just going to leave because there's no pressure for it to leave. So the quality of ducting and the quality of installation really does matter. Thanks. Yeah, summer bypass. So Patrick is asking, can you discuss the use of summer bypass, for instance, in a home without cooling in an area like Tahoe? Tahoe is a good area to talk about that. So summer bypass is designed to kind of take care of a unit that works really pretty well in all climates. And imagine that outside it's super hot, maybe spring or fall or something like that. And inside, you're trying to maintain, a good steady temperature. So I'll say, 87 degrees outside, and we're trying to hold it at 70 inside. But because of the way the sun works and our building envelope, we've got airflow coming in, and we're redirecting kind of the excess temperature out. So that's not so bad. But the whole building envelope heats up just because the sun's hitting it, and it's an average structure. So we wind up overheating, and long about 3 o'clock, we've we've reached our highest temperature inside of the building envelope just by solar radiation. And so now it cools down, and we get into the evening, and that 87 degrees in the shoulder seasons will drop down to, 60 or something great. And we can open the windows and bring some of that cool air in, but we actually want our ventilation device to kind of pay attention to the climate that we're in. And so when it's cooler outside, and we're trying to be 70 inside, but we've climbed to 76 or 78 or 80 or something like that, now we've got a core in the middle, and that core is going to try and keep that space 80. It's going to do the best job it can. And that's kind of the last thing we want it to do. So what happens with summer bypass, the better units have this employed. And essentially what they'll do is they'll watch for this condition, and they'll watch it 24/7, and they'll say, oh, okay, I I know what my set point is inside, and it's 70 degrees, but I'm 78 or I'm 80. I'm way above my set point. So I want to find ways to work it down. It knows what the outside air temperature is because it's got a temperature meter, thermistor, kind of right where the air comes in. So it knows that it's cooled down to 62. So essentially, what it does is it opens up a little flap, and it takes this return air temperature coming back from kitchens and baths that's like 78 or 80, and it redirects it around the core directly to the outside. So when it goes around the core directly to the outside, this stream of air doesn't still flows through the core, still flows through the filter in front of the core, but it doesn't go through heat recovery. So if it's 62 coming in here, it's going to be 62 coming in here. It'll keep flowing in the house until the house sees a temperature drop from the 78 or 80 down to its set point of 70. And then it'll say, okay, yeah, I'm back in business. Let's turn off this summer bypass and go back to being an HRV or an ERV. And then it'll go back and try to maintain that temperature because that's its kind of target. So in the better machines, that's called summer bypass. In the commercial world, that's called an economizer. And it's just basically looking at the conditions and kind of setting operation to suit the conditions. Um, okay, so Laura, yes, I was late to the presentation, so my apologies. Yeah, no worries. If this was already covered in a home with separate small apartment attached. Um, so Laura, there's not one answer for that. Um, here's a slide where we did kind of talk about this. Um, so we can have an apartment. We can have a situation where we have an apartment building with 5 shotgun studio apartments in it, or one big home with one really good HRV and a small one-bedroom apartment or something like that that's a rental unit. So the two ways are totally fine, um, and everyone's got a different answer. We want a good HRV in both circumstances to get the benefit of that and the filtration and all of that. So if you're in a climate where and you have an installer that's comfortable running some steel ducting up to that firewall separation and running it through a smoke damper, then that's fine. You can drop into that apartment. You need to do it for kind of the supply flow and the return flow, and distribute it in the apartment, bring it back. In the good HRVs that don't use recirculation, no one will ever be in a situation where somebody's bath flow is coming back into their supply flow. And then we also have situations where in all markets, people use too. It's easier. You don't have to deal with the fire regulation. You don't have to deal with an inspector who's maybe unfamiliar with what the requirements in that jurisdiction are to send ventilation air through a fire separation. So it's real simple. So you could use a smaller device, and these things come in large, medium, and small. There are units that are small enough to ventilate a single studio that have 90% effectiveness and MERV 13 filters on the intake. Um, Cost wise, it's actually pretty similar. Sorry, fire dampers are expensive. They're expensive to put in, and the separate units are also have some cost to them, but it's easier because when in planning you can just plan for that small apartment, and inspection you're inspecting for that small apartment, so there's no, there's a little less dialogue for building permit and a little less for inspections. um, Panasonic ERV in the past. Okay, so Scott, I have to say that Small Planet Supply, we sell the Zender equipment, and the Zender equipment is super good. We use it on passive house projects, and that's kind of where our we really kind of developed ourselves. Um, I know so Panasonic does make a good one. They make some 60 CFM ERVs that you would kind of put in a bath in a hallway, and those really aren't very good. They're kind of sorry. Um, I mean, they were designed at a time to deliver some ventilation and enthalpy recovery. Um, and they're a small kind of unit with a couple of ports on it, but they also make a really good unit that if you look up the HVI specs on it, it's like 85% effective or something like that. And it's a pretty good one. So the Zender units that we work with are literally about the most efficient in the world. They're plentiful. There's lots of them in California. There's some in these pictures. For large buildings, we also work with a company called Ventacity. That's kind of the upper echelon of the market right now. And we're in a position in the industry where most of the industry was built in Canada in this kind of like 60 to 70% recovery range, because that's kind of where they settled on. Meanwhile, Europe kept racing ahead, seeing how good we could make this stuff. Um, so, so I'd say what we're used to right now in North America is probably changing over the next 5 years, probably really quickly. How's that? You missed a question before that. Thanks. Are there any high efficiency ductless HRVs you'd recommend for retrofits with no space money for ducted systems? Yeah. So we've got one, and a company called 475 has got one. They're both great products. The one we have is called a Zender Comfortware 70. This is actually the core out of it. This is actually the filter out of it. Single penetration through the wall. Need some wall thickness, but you can kind of build that out on the inside. Two separate flows of air running across filters, and you have the ability to take one flow and run it into another room. Like you can be in a studio, single penetration through, and then run a couple of ducts over to a bathroom, pick up the exhaust flow there, supply it directly into the main space for the fresh air supply. The other one from 475 is called a sorry, I'm struggling to kind of come up with the name right now. Same thing, single penetration through the wall. You use them in pairs. They kind of talk to each other. One's kind of pulling in, the other one's supplying out. They do it intermittently. They use a ceramic core, pretty good recovery area. And you can find it at 475.com or smallplanetsupply.com. I want to give two recommendations. Yeah, anything else? Good. So with that, I'm going to kind of get back to the end of our slides. And okay, so we're still kind of at the end. Answer questions. So really right now, I've kind of covered all the topics. For those that want to talk um, about more passive house, yeah, straight up passive house ventilation, that's going to be the next workshop. It's going to be on March 30th. And as we get into passive house ventilation, which HRVs, ERVs, we're going to talk about kind of the best performing HRVs, ERVs. We're going to talk about what the requirements for distribution are. And we're also going to talk about how it models into an energy model, and what the passive house requirements are, both North American and the PHI German um, um, Institute. And with that, I think I'm ready to kind of turn it over to Sean and hand it off. Hopefully, this was useful for you, and I appreciate your time and joining and questions. Thanks.
Awesome. Thank you so much, Albert. So much covered today, I think, and lots of questions coming in. So I think folks found it really valuable, and I appreciate it. I'm going to launch a quick just meeting usefulness poll. Please take it for 4 questions. It really helps us out. But why don't we just, since we're over time, why don't we just skip to the last upcoming event slide, and I'll just say a few words and then let everyone go.
Yeah, thanks. Good.
Perfect. So one, just contact me. My email is up there on the screen. If you are interested in AIA learning units for this course and you're not sure you provided your number at registration, we'll get you those. We'll send you a follow-up email with some slides and the recording today if you want to reference anything. Then we have a few courses coming up next week, touching on some electrification ideas, again, kind of around some small appliances for zero net energy buildings, and then electrification specifically for the energy code. Beyond that, we have passive house retrofits if you're interested in continuing on the passive house kind of series, and we'll touch on some ADUs coming up in here in March. But thank you for filling out the survey on your screen right now. That really helps us. There'll also be a quick survey in the follow-up email. We're putting together our Q2 calendar, and if you're interested in more courses from Albert and Small Planet Supply, please let us know what you're interested in. That really helps us out. But with that, I just want to say thank you to Albert. Super informative. Your expertise really shone through today, and grateful for having you here with us. And thank you all for joining up too. And thank you to Small Planet Supply. I know the crew works hard as well to get the trainings going as well. So with that, I'll let everyone go, and thank you so much for joining us. Thank you, Albert.
Welcome.
All right.